Hello students, today we are going to discuss about the velocity of transverse wave in a stretched string. So consider one string, okay. So consider this is the one string. This one string is attached, one end is attached with or one end is fixed, okay. One end is fixed with any one substance and in another one end is in your hand. Just you are here, okay. Just you can oscillate this string. So what happened? So this string moving like this, okay. Suppose if this end is not fixed, okay, so this end is not fixed, then this string is moving like this. So consider one stretched string. Now you can oscillate or give some external force, so it will be moving like that, okay. This is the waveform, okay. So this will be moving in a like a wave. Now here this wave is moving like this, okay. So this wave is moving. Here one observer is there. Here one observer is there. This observer moving, this observer is also moving. This observer is moving along with the wave. So the velocity of wave and observer wave, velocity of wave and observer wave both are equal. So both are moving at the same velocity, okay. Both are moving at the same velocity means the observer, when the observer look at that wave is stationary. The wave is stationary. When the wave is moving, okay, when the wave is moving, at the same time the observer is moving, both are having the same velocity. So that time when the observer look at that wave, the wave, so what he feels? He feels that the wave is stationary, okay. So from this statement, the wave is stationary. So consider this wave. I am going to take one small part of this wave, okay. I am going to take the small part of this wave. So this wave wavelength, this string wavelength is, the string length is L and mass is M. I am going to take one very small part. This is one small part. This small part length is dl and this small part mass is dm. Because a very small part, the mass will be varying or the length will be varying. So only I can take in the differentiate form. dl is the length of the segment length and dm is the mass of the segment. Okay, do you understand, ma? Okay. Then next, I am going to calculate that linear mass density. Linear mass density. Density means, what is that? Mass per unit volume, that is called as a density. Here linear mass density, that is mass per volume. That mass is dm and length is dl. Mass per unit length, that is called as a linear mass density. Mu is called as a linear mass density. Mu is a symbol for linear mass density, that is equal to dm by dl. Then dm is equal to mu into dl. So how to find out that mass? Because the wave is moving like that, okay. So total that was strength, the string mass we have to easily find out. But I am going to take this part or this part alone. So this part we want to calculate that mass means. So how to calculate? We can multiply with the linear mass density and the change and segment length. So we can get that mass, linear mass. Okay, do you understand? Then dm is equal to mu into dl. So from this way, going to this spot. The spot is AB. Okay. So going to take this spot alone. Like this spot alone. So consider this is the point AB. So this will be like a one circle. This will be like a one circle. Circle means it having that radius. That radius is R. This radius. So this will be a arc, a circle of arc. Okay. So I am going to draw that circle. So this circle radius is R. Now this will be a straight line. Okay. So this point I will take that from this point alone. This segment. So A and B. Now joining this point. So this is called as a radius R, not R. Okay, so this is the radius R, and it will be make an angle. So the whole angle is make an angle is theta. Okay. Now I am going to calculate that sin theta. So this is the dl. The length of segment is dl, and this opposite part is r. Okay, hypotenuse part is r. Then you can calculate that sin theta. Sin theta is equal to what is the formula? Opposite side by hypotenuse. So opposite side, what is that? Dl by hypotenuse r. So dl by sin theta is equal to dl by r. Here theta is very small, so sin theta is substitute panna. The sin theta is also very small, so we can get theta is equal to dl by r. Then sin theta is very small, so sin theta is equal to theta. Then theta is equal to dl by r. So this is the equation number 1, and this one equation number 2. dm is equal to mu into dl, and theta is equal to dl by r. Okay, then next this circle. So this will be a moving. This is our circle. So like this is the moving like this. Okay. So here the centripetal acceleration is acting because this point always towards the center. This point is always towards the center. So centripetal acceleration is there. That centripetal acceleration we are going to calculate. So centripetal acceleration ACP is equal to, already we know the formula. What is the formula? V squared by R. Centripetal acceleration is equal to V squared by R. And we are giving the one force, then only it will be moving. Okay. Suppose that force is called as a centripetal force. So that centripetal force CP is equal to, what is the formula? mv squared by R. Here dm v squared by r, because here we can take that one small segment of mass alone. So only I can take the dm alone. Actually the centripetal force formula is mv squared by r. Here I am taking that very small mass alone. So that's the reason I am taking dm. So F centripetal force is equal to dm v squared by r. Then centripetal force is equal to dm is equal to, what is the formula? Dm is equal to mu into dl. So you can substitute mu into dl v squared by r. Then centripetal force is equal to mu into dl v squared by r. So I can write this side. FCP is equal to mu dl v squared by r. Then next, from this diagram, radial force, I am going to calculate the radial force. This is the centripetal force. Next one, radial force. So this is R radius. This part. And radius is R, the center point is O. Going to draw a each side, joining this side. So this will be an theta. So the whole is called theta. And taking this alone part. So theta by 2. And so this part is theta by 2. This is theta. So this theta I am going to divide in two parts. So only I can take that theta by 2. Then here, so this is the bending. Okay. So that curve is bent. So which direction we don't know. So this part I am going to divide it in two equal parts. So what are the parts? One is the horizontal component part and another one is the vertical component part. That horizontal component is called as a cos theta. So here F or cos theta. Here theta is the theta by 2. So I can take this part is theta by 2. So this part is theta by 2. R cos theta. So R cos theta by 2. So this will be a tension, not R, tension, because this curve. So how much tension? Tension will be acting. Okay. So T cos theta by 2. And this one T sin theta by 2. This is the horizontal component and this one vertical component. And like this, so here also here also it will be divided into two parts. One is the T horizontal component, there is the T cos theta by 2 and the vertical component T sin theta by 2. So here two parts, T cos theta by 2 and T sin theta by 2 at the point A, and this is the point B, T cos theta by 2 and T sin theta by 2. So both T cos theta by 2 and T cos theta by 2 at the point A and point B. So horizontal component equal but opposite direction. So we can sum up these two components, we can get that 0 because both are in opposite direction but equal value. So T cos theta by 2 minus T cos theta by 2. So this will be equal to 0. So I am going to adding this vertical component alone. So that radial force is called as a radial force. Radial force Fr is equal to T sin theta by 2 plus T sin theta by 2. So what we can get? So adding this two value T 2T sin theta by 2. T sin theta by 2. Okay. So radial force F R is equal to 2T sin theta by 2. So this radial force is equal to the centripetal force. So what is the centripetal force? Mu dl V squared by R. So this radial force is equal to the centripetal force mu dl V squared by R. So Fr is equal to Fcp. Then 2T sin theta by 2 is equal to mu dl V squared by r. From this case, theta is a very small. So sin theta by 2, there is also equal to sin theta by 2 is a very small. So this is equal to theta by 2. You can substitute this equation. So 2t theta by 2 is equal to mu dl v squared by r. So 2 cancel. So we can get t theta. T theta is equal to mu dl v squared by r. So theta is equal to, what is the formula here? The theta is equal to dl by r. So that value you can substitute. So t into dl by r is equal to mu dl v squared by r. R cancel and dl cancel. So remaining part we can get t is equal to mu into v square. Then v square is equal to t by mu. Then v is equal to square root of t by mu. So here v is the velocity. The velocity of stretched string is directly proportional to the square root of tension at the given linear mass density. And the velocity of the stretched string is inversely proportional to the square root of linear mass density and independent of shape and size of the wing. So the velocity only depends upon the tension and linear mass density. Okay, do you understand, ma? That's all. Thank you.